Okay, so the second part of part 1 of 6.3 is that now that we've learned this language of initial side and terminal side, and that the terminal side can be in any quadrant, now we're going to start looking at triangles in any quadrant. And then 6.3 part 2 we'll start finding exact values of these different triangles. So reference triangle is the triangle that's made with the terminal arm and always the x-axis. This is never going to change. So what I want you to notice is that instead of us having a triangle just sort of drawn and not really caring where it is, we're putting it in quadrant 1, 2, 3, and 4. We're also drawing a circle that intersects your terminal arm at a point xy. Okay, so this is always what we're going to do. We're going to have this terminal side. We're going to have a point on the terminal side that's going to intersect a circle so that our circle can have a radius. So from this vertex to the point, right, where the terminal side intersects a circle, you're going to have this length r. Every single triangle, whether it's in quadrant 1, 2, 3, 4, is going to have this length from the vertex to the edge of the circle, which is going to be the radius. So every single circle has a radius. Also, because we're intersecting at a point xy, every single triangle is going to have an x value, which is going to be the length along the x-axis, and a y value, which is the height to where you're going to intersect the circle. So what we are going to now do is change terminology. So with triangles, we've always said, SOHCAHTOA, opposite adjacent hypotenuse, because every single triangle we drew was acute and it didn't matter where it was in space. But all of a sudden now, if we start going into this coordinate geometry, okay, we are going to say that if we were to label this triangle, angle theta is in this corner, so this is always the hypotenuse. From this angle, this is always the opposite, and from that angle, this is always the adjacent. So if we write this in terms of x, y's, and r's, the hypotenuse is the radius, the y value is your opposite, and the x value is adjacent. Well, let's look into quadrant 2. If angle theta, now angle theta read in standard position is from the initial side to the terminal side, but we're actually going to be talking about angle theta being in here because this is a reference triangle for that angle, and that angle is going to give you a value that's important in a bit, okay? But from this angle, y is still my opposite, r is still my hypotenuse, and x is still my adjacent. In fact, no matter which quadrant it's in, okay, so again here, if we put theta as the angle in the reference triangle made with the x-axis and the terminal arm, or the terminal side, sorry, then the y is going to be the opposite, the x is going to be the adjacent, and the r is still going to be the hypotenuse. It doesn't change. Quadrant 4, if we say theta is the angle between the terminal side and the x-axis, y is still my opposite, x is still my adjacent, and r is still my hypotenuse. It doesn't change. So now, because we're going into this coordinate geometry, instead of talking about opposite, adjacent, hypotenuse, we can write the ratios in terms of x, y, and r. Now, does not matter. If you want to always think opposite, adjacent, hypotenuse, cool, okay? You will not be disadvantaged, but you can get things faster if you recognize that sine theta, instead of being opposite over hypotenuse, we can now label as y over r, where r is the radius of the circle and y is the y value of the coordinate point. If sine theta is y over r, then I know that cosecant theta is r over y. Now what I want you to do is then fill out these other 4. So what would the ratio be in terms of x, y, and r? So cos theta is adjacent over hypotenuse. Adjacent is x, hypotenuse is r. So secant theta would be r over x. Tan theta is opposite over adjacent, so y over x, or x over y. So now what we're going to do is exactly what we did in 6.1, right? We are going to be finding the 6 trigonometric function values, but this time for an angle in the third quadrant. So we're no longer looking at these acute angles. So how are we going to do this? Well, we know that sine theta is y over r. So sine of this angle is going to be the y value, which is -3, over the r value. They didn't give it to us. They gave us the point at which the terminal side intersected the circle, but they didn't give us the radius. So we need to find it. Same thing as 6.1, we're going to use Pythagorean Theorem. R squared is going to equal, now since we're finding the hypotenuse, we're going to take the sum of the squares of the other two sides. So -3 squared plus -4 squared, which gives us 9 plus 16, which is 25. So that's what R squared equals. So to find R, I'm going to take the square root. Don't forget, when you take the square root, it's plus or minus the square root of 25, or plus or minus 5. Then you have to look at the context. In 6.1, we were always looking at them as acute. So we always looked at them in the first quadrant, so we knew that positive was always the answer. As soon as we moved into quadrant 2, 3, and 4, that's not always the case. But the radius. The radius is a length. It's the length of the distance between the vertex and the edge of the circle, and it can never be negative. So radius is always positive. That one's nice. So now I know that sine would be -3/5. So if I wanted to find cosecant theta, instead of being y/r, cosecant theta is r/y. So I would do 5/-3. But that will not be the answer when you check your answers in the back of the book. Why? Hopefully you're yelling at the TV or the computer that math doesn't like negatives in the denominator. So even though we know that in this scenario, it's the y value that's negative, it's not attached to it in a fraction. This is -5/3, meaning it's just a negative fraction, or you could write it as -5/3. So even though the 5 wasn't the negative value, when you put it into a fraction, the negative sign is often written with the numerator. So don't get attached to the negative sign being with whatever number it's with. It will always go in the numerator, but it might have belonged to the denominator, right? This 3 is what's negative, and yet when I write my answer, I'm going to write the 5 as negative because it's just the fraction. Like that 3 being negative made my fraction negative. Okay, so now I want you to continue. I want you to find cos theta and secant theta. Pause the video and go. Okay, so cos theta is adjacent over hypotenuse, or x/r, so it's -4/5. So secant theta would be -5/4. Then we move on to tan theta. Tan theta would be opposite over adjacent, or y/x, so it'd be -3/-4, which we would write as +3/4. So cotan theta would be 4/3. One thing I want to point out is that whatever the sign of sine is will be the sign of cosecant. Whatever the sign of cos is will be the sign of secant. Whatever the sign of tan is will be the sign of cotan, right? They will have the same negative or positive value. So if sine is negative, cosecant is negative as well. Cosine, both are negative. Tan, both are positive. Okay, moving on. So now a step up from that is that the questions in the textbook will say as follows. A function value and a quadrant are given. So this is your function value. This is your given quadrant. Find the other 5 trigonometric values, give exact answers. So they already gave you that sine theta is 2/3, which means we already know that cosecant theta is 3/2, right? Without any work, we know that cosecant is just the reciprocal. But now we need the other 4. So we want to find cos theta. Well, I don't have enough information. I know y/r, but for cos theta, I need x/r. So I know it's going to be over 3, right? But I don't know what the other one is, so I have to figure out it. So I'm going to have to use Pythagorean Theorem. But to do that, the first thing I want you to do is sketch it. They're going to give you what quadrant it's in because they want you to determine the sign of your unknown value. So sine theta is equal to 2/3. Remember, theta is always an angle made with the x-axis. So we're going to put theta in here. We know that the opposite, or the y value, is 2. And we know that the hypotenuse, or the r value, is 3. Now looking at this, okay, one thing I want you to look at is when you see this diagram, is this y value positive? Is the 3 positive? Well, this is the positive direction for y. So yeah, 2 should be positive in quadrant 2. Radius is always positive. let's solve for x. So x squared equals, remember, c squared equals a squared plus b squared, right? The hypotenuse squared equals the sum of the other two sides squared. So if I want to solve for a side, you have to take the hypotenuse squared and subtract the other side. So to find x squared, I'm going to do 3 squared minus 2 squared. So I get that x squared equals 9 minus 4, which is 5. So x equals plus or minus root 5. Now I have to decide which answer is correct. Because my angle's in quadrant 2 has negative x values. So I know that this is going to be negative root 5. So now when I fill out cos is x over r, so it's going to be negative root 5 over 3. Secant, you just take the reciprocal. So again, when you take the reciprocal, 3 over root 5, the negative's just going to stay on the top. But you have to rationalize your answer, your denominator. So multiply by root 5 over root 5 gives me negative 3 root 5 over 5. Okay, now we're going to do the same thing with tan. Tan theta equals y over x, so 2 over negative root 5. Then you're going to rationalize your denominator. So again, I would move that negative sign up to the top so it doesn't confuse you. So I'm going to call this negative 2 over root 5, even though it was the root 5 that was negative. I'm going to multiply by root 5 over root 5. And tan is going to be negative 2 root 5 over 5. Cotan theta, instead of being y over x, is going to be x over y. So it's going to be negative root 5 over 2. And that's my final answer. So those are my other 5 trigonometric values with exact values. Don't touch a calculator. All right, that's the end. So that was 6.3 part 1. I know it was short, but when I was looking at 6.3, what we're about to do now is take a totally different turn. So this is kind of a nice introduction. Treat it as a bit of a catch-up day, and then we'll do 6.3 part 2 next.